Okay, so this next case is basically looking at an example of when we can use the integral in figure B rather than this one, which means we have fewer residues to evaluate. So if we're trying to find this integral from 0 to infinity of b times f, and f is even, and b of x is such that b of minus x is some multiple of b of x, where that multiple is not allowed to be minus 1. So in other words, b is not allowed to be an odd function. And some other conditions. So b times f has to vanish for large enough z, and also that it's not allowed to have any poles on the real axis. And finally, we need this condition as well. Then it turns out that you can evaluate this integral in this way. Again, don't try to memorize this formula. It's easy to obtain the answer to this integral if you just remember what kind of contour to use and use the usual methods. Okay, so we're going to use this semicircular contour and let the integral we want, we'll call that I, so that's from 0 to infinity of b times f. Okay, so if we use this contour, we've actually already said that, it's a limit as r goes to infinity. I forgot to put an r here. And epsilon, which is this distance here, goes to 0. Then the integral we want is this one along here. Then as long as b times f goes to 0 fast enough, then this will vanish. Again, this is a very quick way of doing things. The important thing is this integral along here, so we'll look at that more carefully. Okay, so the integral along here is well, we put z equals x again, but we can make the change of variable x equals minus r. Since obviously x is negative and we want r in polar coordinates is always positive. Okay, so we make that substitution. Then this becomes an integral from 0 to infinity after we change the limit sign and add a minus sign and so on. We've already said that b of minus x is equal to alpha of b of x. So anyway, you can check. Okay, if we swap the limit, okay, so we're going to have to swap the limits. We're going to change variables. If you add up all the minus signs, you end up with 1 plus alpha times I. So, I mean, the reason for choosing a symbol B is sort of B for branch cuts. I mean, basically this is used obviously when B itself has a branch cut. So all of this will become clear hopefully in the next example. I've chosen this example. This might not be the easiest way to do the integral, but it sort of illustrates how this could work. An easier way would probably be just to change a variable, but okay, we're going to try this with using this contour here. Okay, so this example shows in detail how you should evaluate what sort of working you should show for doing this type of integral. Okay, so we're going to use this contour here, basically because we have an even function multiplied by a function with a branch cut along the real axis, which is obviously not an odd function. So we use this contour, let r go to infinity and epsilon, this distance here, goes to 0. So we've got I, the integral we want. We've got this semicircular integral around here. So theta now is from 0 to pi. This is our usual dz in polar form for changing theta constant r. Similarly, this is this little quarter circle here. We're integrating theta from pi to pi by 2 anti-clockwise. And finally, we've got this integral here. This is the important one to get right. So we've already made the change of variables, x equals minus r. So dx changes to minus dr. X squared obviously stays the same as r squared. And when we take the root of x, well, then, effectively we've got z. So we're writing z in polar form now. Z is e to the I. Z is r times e to the I pi, which is what we've got here. Remember the angle. If you've got a branch cut here, all angles are between 0 and 2 pi. So along here the angle is pi. Okay, so this integral and this integral go to 0. We can show that easily as r goes to infinity. You've got r divided by r squared, so you've got 1 over r, and you've got another root r here, so it's order r to the minus 3/2, that goes to 0, no problem. And this thing here, as epsilon goes to 0, well, you can forget this. You've just got epsilon divided by root epsilon, so that goes like root epsilon. That also goes to 0. So the third integral, so we said we write z equals r e to the I pi, is just a multiple of the integral we want to find. We can take out the root e to the I pi is, remember it's always a positive square root, so it's just e to the I pi by 2, which is simply I. So you've got an I on the bottom. Which you can also write as e to the minus I pi by 2. That's the same as 1 over I, or yeah, minus I, same thing. Okay, so this is simply, yeah, e to the minus I pi by 2 times I. Okay, so we need to evaluate the pole. So this function here is going to have a pole at z equals IA. So residue of that, again, you have to be a little bit careful with evaluating residues when you've got branch cuts or when you've got square root and things like that. Anyway, we're going to have use a simple pole p over q dash method. So the q is a squared plus z squared, so that gives us 2z. So that's the 2ia, and z equals ia. So we write that in polar form, and we get z equals a times e to the z equals e to the I pi by 2. So taking the square root of that gives us e to the I pi by 4, and it's 1 over, and it's a square root of a, so that gives us the a to the 3/2. And yeah, it was I z equals IA, so that's where the I came from. Okay, so the integral is 2 pi I times the residue. And that's, sorry, this thing is 2 pi I times the residue. It's not quite equal to the integral itself. The integral itself is I times 1 plus e to the I pi by 2. So this is our final expression here after we've cancelled 2 pi. We're multiplied by 2 pi I. Simplifying this, we multiply top and bottom by e to the I pi by 4. That cancels this out, and we end up with e to the I pi by 4 plus e to the minus I pi by 4, which is 2 over cos pi by 4. Sorry, it's so that's equal to 2 cos pi by 4 on the bottom, and then, well, cos pi by 4 is 1 over root 2, so you end up with root 2 on the bottom. Okay, so as I think I mentioned before, this is not the simplest way of evaluating this integral. You can always change variable and then you don't have to worry about the branch cuts. But anyway, it's just to illustrate the method. Okay, so you can now do question 28.